In December 2022, something extraordinary happened inside a lab in California. For the first time in human history, a nuclear fusion experiment produced more energy than it consumed. No pollution, no carbon emission, just raw power. Create the same way stars are born. Some call it a turning point for humanity. Others called it overhyped. So what actually happened? And could nuclear fusion really becomes the answer to our energy crisis? When most people hear the words nuclear, they think of nuclear fission, the technology behind today's nuclear power plants. Fission works by splitting heavy atoms apart, releasing energy in the process. It's efficient but deeply flawed. The fuel is radioactive. Accident while rare can be catastrophic, and the waste remain dangerous for thousands of years. Fusion, however, works in the opposite ways. Instead of breaking atoms apart, fusion forces them together. Two light atomic nuclei merge into one heavy nucleus, releasing an enormous amount of energy. This is the process that powers the sun, every star in the night skies, and potentially our future power grids. The promise of nuclear fusion is difficult to overstate. The fuel form of hydrogen is abundant and widely available. The reaction produces no greenhouse gases, and unlike fission, fusion doesn't generate long-lived radioactive waste. If fusion can be scaled, it could provide near limitless clean energy. It could reduce our dependence on fossil fuel, slow climate change, and offer long-term energy security to a growing world. On paper, fusion looks like the perfect solution, but reality is far more complicated. Fusion is incredibly hard to achieve. Atomic nuclei naturally repel each other. To force them together, scientists must heat fuels to temperature hotter than the core of the sun, millions of degrees Celsius. As these temperatures, matters become plasma, an unstable, superheated state that no physical material can touch without being destroyed. Even if those temperatures are reached, the plasma must be held together under immense pressure, long enough for fusion to occur. But the hotter the plasma gets, the more violently it tries to escape. Controlling it is one of the hardest engineering challenges ever attempted. And that's only part of the problem. Fusion research is expensive, extremely expensive. Reactors are massive. Material must survive extreme heat and radiation. And experiments can take decades to refine. Critics argue that fusion has always been 30 years away. They question whether the billions spent on fusion would be better invested in renewable energy source. We already know how to scale, like solar, wind, energy storage. So why keep pursuing fusion at all? Because fusion is no longer just theoretical. One major approach is magnetic confinement, where powerful magnetic fields trap hot plasma inside donut-shaped reactors called tokamak. Another is inertia confinement, the method used in the 2022 California experiment. In this approach, tiny pellets of hydrogen fuels are compressed using powerful lasers. For a brief moment, the condition became extreme enough for fusion to occur. That moment was short, but it mattered. For the first time, fusion crossed a critical threshold, net energy gain. It proved the physics works. Fusion is still not ready to power cities. Reaction must last longer, efficiency must increase, and material must be developed that can survive years of constant stress inside a reactor. Costs must fall dramatically before fusion can compete with existing energy sources. These are not small problems, but they are engineering problems, not impossibilities. Nuclear fusion won't solve our energy crisis tomorrow, and it may not replace renewables anytime soon. But for the first time, fusion is no longer a distant dream. It is a working idea, slowly moving from the realm of stars into our own world. If humanity succeeds, fusion won't just change how we generate energies, it will change how we think about our future on this planet. And that possibility alone is worth paying attention to.